All right, so the derivative affects the shape of the graph in a variety of ways. We've already seen that the derivative affects the shape of the graph in terms of increase and decrease. Today, we're going to focus on how the derivative of the graph is affected for concavity and where we can find points of inflection. So we previously started with the first derivative test. Now what we're going to look at is the extension of the first derivative test. So the first derivative test said if the first derivative is increasing, then the second derivative is positive. If the first derivative was decreasing, then the second derivative was negative. So intervals of increase and decrease on the original told me the values of the derivative. The same holds true with the derivative of the derivative. So if the first derivative is now increasing, then our second derivative is positive and the original is concave up. If the first derivative is decreasing and the second derivative is negative, then the original is concave down. So instead of using the definition of concavity to determine whether a function is concave up or concave down, we can use an application of the first derivative test on the first derivative. So we call this the second derivative test. And the second derivative test says that the graph of a twice differentiable function is concave up on any interval where the second derivative is positive, and it's concave down on the interval where the second derivative is negative. The second derivative test can be summed up by the following pictures. Well, this is somewhat humorous because if it's concave up, it's a smile and it's positive. It's concave down, it's negative. So it's easy to remember concave down looks like a frown, and usually if you're frowning, you're negative or you have a bad mood. And if you're happy, you're positive and you're in a good mood. So you can kind of remember positive to happy to concave up, negative to mad to concave down. A point of inflection is a point on the graph where a function has a tangent line, even if it's a vertical tangent line and where the concavity changes. So we find points of inflection by finding where the second derivative equals 0. We find them where the second derivative equals 0 or does not exist. We find them where the second derivative equals 0 or does not exist. You are not guaranteed that the function has a point of inflection at this point. The second derivative has to change signs in order for a point of inflection to occur. So just like on the first derivative test, in order for a function to have a max or a min, the function had to change from positive to negative, or from increasing to decreasing, or vice versa. I had to go from decreasing to increasing, or negative to positive on the first derivative test. On the second derivative test, a function must also change signs in order to be a POI. So we call them critical points for the first derivative test. On the second derivative test, we're going to call them PPOIs. PPOI stands for a potential point of inflection. So you may see me write PPOI, possible or potential point of inflection. So we don't call them critical points on the second derivative test, we call them PPOIs. We can create then a connection between f prime, f double prime, and our graph of f. So we can use the same graph we talked about the other day. Here we have a graph of a cubic function. It has intervals of increase and decrease. It has intervals of concave up and concave down. It has potential PPOI, where it changes from concave down to concave up. We have extremas and we have zeros. So graphs now, when we talk about them and we look at them, they have so much more potential than just a cubic function. So we're going to use the graph as our previous example gave and indicate which portions of the graph are concave up and which portions are concave down. And then we're going to label them. So this graph is concave down, where it looks like a frown, which is from here all the way to about there. Because right here, you'll notice that the derivative at this PPOI is a vertical tangent. The derivative is going to become 0 on that second derivative. And then our graph is concave up beyond that point of inflection through there. So applying the second derivative test, we can talk about how we could see this. So this graph right here would represent f prime. This is the graph we drew in our notes on Tuesday. So this graph right here represents f prime. The zeros of the graph occur at the extrema of the original. So there's my zeros at the extrema. Now, what's important to note is this new point down here. The extrema of f prime occurred at the point of inflection. The extrema of f prime occurred at the point of inflection. This is happening because of our rules and how they relate to derivatives and their zeros. So, using that previous graph, let's sketch the graph of f double prime. So everywhere the original graph was concave down, f double prime needs to be negative. Everywhere the derivative was decreasing, f double prime needs to be negative. The local min, or the extrema of the derivative, or the POI of the original, is going to be our 0 of f double prime. So it's going to occur at 3. And then if you think about a rule of thumb, a cubic derives to a quadratic derives to a linear. So this is going to be a linear that's positive to the right and negative to the left. Now, whatever slope you drew in, you have to draw in both ways. We don't actually know the slope of this function. It looks pretty much to be not stretched or compressed in any way, just shifted. So I went with a slope of 1 on my linear graph. So that's a graphical representation of the first and second derivative test. Let's look at it analytically. So we're given a function. Our function is a cubic, just like the previous example. So a cubic function can have at most 3 zeros, which means the derivative can have at most 2 critical points. We want to find concave up and concave down. Well, the only way to get to concave up and concave down is to find the second derivative. So we're going to find f prime of x And then we're going to find f double prime of x. And we're not actually doing anything with f prime of x this time. We're just moving on. And in order to find intervals of concave up and concave down, we have to find the PPOIs of f double prime, which occur when it equals 0 or does not exist. So that's at x equals 1. And then we're going to put these on our number line, and we're going to look at 1. And then we're going to look at the signs to the left of 1 and the signs to the right of 1. So to the left of 1 is 0. If I plug 0 back into f double prime, I get 12, which is positive. If I plug in 2, I get negative 24 plus 12, which is negative. So what that means is that on the original graph, it is concave up from negative infinity to 1, and concave down from 1 to infinity. And because we had a sign change to the left and right of 1, that means that 1 is a point of inflection. Example 2. We have f of x equals x minus 4 square roots of x. Where's the graph concave up? Where's the graph concave down? So we're going to find f prime of x. So I have 1 minus 2, x to the negative 1/2. I'm going to leave it in this form until I find my second derivative. Derivative of 1 is 0. Derivative of negative 2 times negative 1/2 x, and this becomes negative 3/2 because we subtract 1 away. A negative times a negative is a positive. 2 times a half becomes 1. So we get 1 over x to the 3/2. Now, thinking back to the original, so everything I do for the original, I'm trying to do in black and then derivatives in red. The domain of this original function is such that x has to be greater than 0 because of the square root. We know we can't take a negative. So the domain of the original is 0 to infinity. And that's something to keep in mind as we look at our PPOIs. So we're going to set the second derivative equal to 0. So you get 0 equals 1 for f double prime of x equals 0. And then we have f double prime of x does not exist. And that's where x to the 3/2 equals 0, which would be when x equals 0. So the second derivative never equals 0, and then the second derivative does not exist at x equals 0. So that kind of creates a little bit of a complication, or it tells me something very important about this function. So let's continue to investigate. We're going to make our number line, and we know on our number line for f double prime that 0 is a critical point, but we also know that nothing exists to the left of 0. So I don't have to worry about plugging a number in to the left of 0. I do, however, have to worry about plugging a number in to the right of 0. So let's plug in something bigger than 0, maybe 1. So if I plug 1 into that second derivative, I get 1 over 1 to the 3/2, which is 1. So I get 1 over 1, which is 1. 1 is positive, which tells me that this derivative is always positive, which means the original is always concave up. So f of x is always concave up on its domain. and its domain is 0 to infinity. So if you wanted to write out where it was concave up, you would put concave up, and you could go 0 to infinity as well. If I had asked you to find potential points of inflection or looking at points of inflection in the case of this problem, there are none. So the graph is never concave down, and there are no POIs. There are no points of inflection because there are no PPOIs in which we can have a sign change. So there are no points of inflection. Now, looking at that same example, we can find where there are points of increase, points of decrease, etc. So we have our first derivative still from the previous problem page. Which was 1 minus 2x to the negative 1/2, which became 1 minus 2 on top, square root on bottom. So it's important to know that 2 doesn't go down with that square root. That's a common error I see students make. They want to drop that 2 down. It's not a 1/2, it's a 2. So then that's also kind of like the square root minus 2 over the square root of x, creating that common denominator. Why I do that is because it's more helpful to find f prime of x equals 0 and f prime of x does not exist. So square root x minus 2 equals 0 and square root x equals 0. So we get x equals 0. And we get square root x equals 2. Squaring both sides, we get x equals 4. So I have 2 critical points, so a CP here and a CP there. And we're going to determine if we have maxes or mins, as well as increase or decrease. So I have 0, 4. We know the domain does not exist to the left. And then we need to look at our signs between 0 and 4 and beyond. So if I plug in 1, the square root of 1 is 1. 1 minus 2 is a negative. And then the bottom is the square root of 1, so it's a positive. So negative over positive is a negative. Plug in something bigger than 4, like 8 or 9. Let's plug in 9 because square root of 9 is easy. Square root of 9 is 3. 3 minus 2 is 1 over square root of 9, which is 3. So 1 over 3 is positive. So it's positive. So what that means is the original function is decreasing from 0 to 4 and increasing from 4 to infinity. And because it changes sign at 4, that means that 4 represents an extrema. And in this case, because it goes decrease to increase, x equals 4 is a local min. And again, we already did the concave up and points of inflection on the previous slide. Okay. F of x equals the cube root of x times the quantity x plus 4. So you have 2 choices here. We can do a product rule, or we can distribute so that I don't have to do a product rule. And I can simply take our derivative as a polynomial-ish. So this becomes x to the 4/3 plus 4x to the 1/3. So I'm just going to distribute that function in. And now f prime of x is 4/3 x to the 1/3 plus 4/3 x to the negative 2/3. So you can take out a GCF of 4/3, and that leaves you with x to the 1/3 plus 1 over x to the 2/3. And again, I really like common denominators, so what I'm going to do is multiply by x to the 2/3 on both sides. So I get f prime of x equals 4/3 x, because 1/3 times 2/3 is 1, plus 1 all over x to the 2/3. And then I'm going to look for my zeros. So I have a 0 at the top when x plus 1 equals 0, which is at x equals negative 1. I have a 0 in my denominator when x to the 2/3 equals 0, or at x equals 0. Now, this time, because it's a cubic, we are allowed to have negatives. So because this is a cubic, we're allowed to have negatives. Therefore, I have no domain restrictions except for you can't obviously divide by 0. So on my f prime number line, I have negative 1 and 0. So we're going to find the signs to the left and to the right. So the sign to the left is negative, in the middle is positive, and to the right is positive. So here's the first case in which we have a derivative where it goes negative, positive, and doesn't change signs, but goes positive again. That tells me that 0 is a critical point, but not an extrema. It's a critical point, but not an extrema. So increasing from negative 1 to infinity, and decreasing from negative infinity to negative 1. And then I only have a relative min at x equals negative 1. There is no max in this case. Looking at my second derivative, so I'm going to open up a new page just because I'm running out of space. So we already talked about the max and mins. Where is this concave up and concave down? So we have to find our second derivative. And just because I know we're running short on time, I'm just going to give you the second derivative a little quicker. So it's 3x to the 2/3 times 4 minus 4x plus 4, because I distributed that 4/3 back in to make it easier. 3 2/3 x to the negative 1/3 all over 3x to the 2/3 squared. And that simplifies and reduces to 4x minus 8 all over 9x to the 4/9. To the 5/3. after you clean everything up. So your second derivative equals 0 when x equals 2. And again, it does not exist at 0. Making our number line, you put on 0 and 2, plug in to find your signs. So it goes positive, negative, positive, which tells me the graph is concave up, concave down, concave up, which means that 0 and 2 are both points of inflection. So in case you have study hall and you want to work on the first part of the assignment for tonight, before we meet back this afternoon and start on the next part, there are a few pages in your textbook. So we're doing 215 and you're finishing out 7 to 12. So again, I have the assignment tabs open up on Fusion, but I don't want any of the homework until we're completely done with all the lesson notes. So like there will be a bunch for 215, so you can put all your worksheets on one file and all your textbook homework on another. That way when we talk about it, check it, etc., it's easier to see. All right, I know the phone rings and I know our times are a little off, so I will see you again at the end of the day and we'll touch base, talk about the quizzes, talk about the other stuff, and I'll see you then.